this is Mr. Coates, and this is APES lecture number 45 on the data that supports global warming. There's lots of data out there. You can find it all over the place. The National Atmospheric and Oceanic Administration has lots of data, and NASA has data. I mentioned the IPCC that has all kinds of data. So there's all kinds of data out there that shows warming. This graph, this is actually in our textbook, and it shows all the different measurements that have been done on things that cause greenhouse gases, as well as the actual temperature itself and sea level, which is one of the most important factors when we're talking about the entire climate change thing, is what's going to happen with sea level. So these graphs over here show you CO2 in concentration, the methane concentration, temperature change over that same period of time, as well as sea level. Now, if you look at the years before present, we go back way far back, 50,000 years, 100,000 years, 250,000 years, all the way back to almost 400,000 years ago on some of this stuff. And so, like, did we have temperature gauges out back before the dinosaurs were around? Did we have CH4 gauges around? Did we know what the sea level? Did anybody measure it back then? Nobody was around. So how do we know about all this data this long ago? And so there's a lot of uncertainty in a lot of this data up until you get to about this point right here. So that uncertainty sometimes leaves room for argument about, against, and also for climate change. And so we want to talk a little bit about where this data come from and how it's used. All right, so historical temperature data. If you look at this graph here, it goes back 10,000 years before present. So it doesn't go back as far as those other graphs, but it goes back pretty far. We can see that there are periods of warming and periods of cooling, and the Earth has gone through these on a consistent basis. When it goes above the actual average here, we call this a interglacial period. When it's below this average, like this one here, then we call it the glacial period. Our last major glacial major ice age here was this one here, a little bit over 12,000 years ago. As we've been warming ever since then, really. We've had these small little periods of cooling, but most of the time it's been mostly warming. So we have these, and we know about these, but the question is, how do we know about them? As we compress some of this data down here, now we're looking back. This is basically the same graph here. So we had the end of the last ice age about 12,000 years ago, and then we've been warming steadily, and we're like this little blip right in here somewhere. And then we'll go over to this graph here, and so basically now we're only looking at about this much data, so we got rid of all this stuff, and so we get a little bit more refined. So if we look at a temperature change starting at this 0 and leaving the 0 at the same spot all the time, we say that where we're at now is we've got a pretty good increase going on here. And if we take that amount of data since 1860, so we're going to stop right about there, we see that temperature was fairly constant in this about area, but then we started increasing, and then all of a sudden it really increased. So this is over the last 130 years, and if you look at this, it looks like we are actually warming up. So what do we know about those older temperatures? How do we know those? Once again, there were no gauges. There was nobody out there with a thermometer. Most of the time, there weren't even people in a lot of areas to take temperatures. So how do we know about these older temperatures? Well, this is pretty good data. What they can do is that they can look at radiometric isotopes of different minerals. They can look at fossils. Certain fossils only grew in areas or only lived in areas with certain temperatures. For example, they find fossils of ferns in Antarctica now. And ferns don't grow in freezing conditions. They grow in very warm, hot, humid conditions. They look at bubbles of ancient air trapped in ice cores. Down here's a picture of a group of scientists. They take ice cores, and they take ice cores that go down thousands, almost hundreds of thousands of years. And they can look in the bubbles trapped within that ice core and sample the actual gases within that, as well as some of the particles trapped within that, and they can look at, see what the Earth's climate was at that point. Can look at ancient pollen samples and compare those to current pollen samples of current living plants. They can look at tree rings. This is an example of tree ring here. This tree came about in 1527, and so this tree goes back not as far as you would want it to, but it goes back pretty far, and so you can look at these tree rings and kind of discern from these how warm or cold or the actual climate was at that point. And then you can look at insects and pollen and bat dung. All these things can be correlated with historic measurements taken since 1861, which is when we really started measuring temperature on the planet with actual devices like thermometers. All these things typically correlate fairly well once we get into this 1861 range. We think that if we get past this, where we don't have actual readings, that these things lead us to a pretty good idea of around about where temperature was. May not be the exact number, but it might be a fairly good estimate. Now, CO2 data. CO2 data has the same problem. Once again, CO2 did not start getting measured until the mid-1900s, so we really don't have a whole lot of direct measurement of CO2 in the atmosphere. However, we can once again sample that air trapped within the ice cores. What they've done here, and this graph is really important, is that we've got several different ice cores here. And that's these three here and this one here. These are all ice core samples. This one is your direct measurement. Mauna Loa in Hawaii is on top of a mountain, and it is the one place on the planet where CO2 is measured and really kept track of on a global scale. All these dark dots here are the Mauna Loa observations since the early 1900s. However, but before then, all we can do is sample the ice cores and look and see what levels of CO2 those bubbles have. And so this is our current ice core data. Now, if we keep on sampling ice cores up until this early 1900 period here, we see that the ice core data correlates pretty well with the actual physical measurements. And so scientists have a pretty good idea that this ice core data is somewhat accurate. It gives us a good estimate of where CO2 was back before we even had any kind of measurements to read it. And if we look here, also the start of this increase here happened right about the time of the Industrial Revolution. So that's one reason why they point to this CO2 data as being very important. Now, as we go on, we're going to see this graph a lot, and you need to make sure that you understand this graph. But it shows the general CO2 concentration on the globe increasing since the 1950s. And this is when fossil fuel use really came into the forefront, when we really started burning all kinds of petroleum and oil and gasoline. So it shows a general increase of CO2 from 310 all the way up to about 370 parts per million in the atmosphere. And this is the measurement at Mauna Loa, Hawaii. It also shows how the temperature has increased as well. So they show a very good correlation here. Now remember, just because you have a correlation doesn't mean causation. So even though they're both increasing, it doesn't mean that CO2 causes the increase in temperature. You could just as easily say that the increase in temperature caused the increase in CO2, if you are thinking that way. So we have to look and see what are the reasons besides CO2 that made this temperature increase. Now, the other thing we can look at is all the emissions of other man-made sources of greenhouse gases. So all of these greenhouse gases, methane, carbon monoxide, ozone, CFCs, all increased 70% between 1970 and 2005. Of course, the United States, China, European Union, Russia were the biggest contributors of CO2. And then the U.S. is also the largest emitter of methane. That's all the feedlots and the agriculture that we do here in this country. China actually emits more CO2 than the United States. However, if we're looking at per person in those countries, the U.S. emits 5 times more carbon dioxide than China. So as I said, the ice core analysis shows the concentrations of CO2 have grown from 280 to 384 between the 1860s and now. And they're mostly blaming this on the increased use of fossil fuels, both coal and petroleum, in those developing and developed countries. Methane emissions have also increased about 60% from fossil fuels. Remember, when we started drilling into the fossil fuel areas, there was methane released, and this methane then can get up in the atmosphere and cause greenhouse effect to increase. Also, livestock, once again, those feedlots, they produce a lot of methane. We saw that in that video previously. Landfills are also another source of methane. When you bury all that trash and rubbish, it starts to degrade underground. And the microbes that are degrading it, they produce methane. And this methane then degasses out of the ground and then can get up in the atmosphere and cause problems with greenhouse gases. Now, the good thing about methane is that it has been leveling off. So we don't see as big a jump increase in methane as we do CO2 in the last 10-15 years. But we think that it's going to increase, and this is why. If you remember when we were talking about energy, one of the types of natural gas out there was a methane hydrate. Methane hydrates are found in large quantities in tundra regions where the ice has locked in those molecules of methane. Well, as the globe increases temperature, that permafrost starts to melt. And then this will release more methane into the atmosphere. As this happens, those methane hydrates will release that methane and will increase the effect of the greenhouse effect. This is what we call a positive feedback loop, because the more methane means the more heating, which means the more melting of the permafrost, which means the release of more methane. In the future, the methane increase is probably going to happen as long as the globe continues to warm. Now, NOx gases have also increased, and this is mostly due to our green revolution when we first started using fertilizers. NOx is one of those greenhouse gases that has also increased. This graph shows methane. Once again, this is that leveling off period that we talked about. But once again, scientists predict that we will eventually increase that. And it correlates pretty good to temperature. As methane goes up, so does temperature. As methane goes down, so does temperature. There is some correlation there between methane, CO2, NOx, and temperature. But once again, correlation does not, in fact, mean causation. Now, the other thing that is really easy to agree with is some of the visual clues out there. There are a lot of visual clues to the warming planet, and some of them include the melting of glaciers. This is a picture of Muir Glacier back in 1948, and it's taken roughly from the same place as this. If you look, this rock here is the same as this rock here, and this mountain back here is the same as this mountain here. In 2004, the glacier had retreated all the way up this way here. And that's a lot of water. There's a lot of water locked up in this glacier. And all of that water has melted and gone into the world's oceans and into the hydrologic cycle. This is not the only glacier worldwide that's happened. In fact, many glaciers worldwide have had this happen to them. Very few glaciers since 1948 have actually grown in size. And so this could be one clue to a warming planet. Another clue, and this is a great graphic too, these are satellite photos of the ice coverage in the Arctic. And the Arctic is mostly ocean here, and in 1979 we had a pretty good ice sheet. This is September, so ice sheet here over Antarctica. And it was almost impossible to take a boat from the Atlantic all the way over to the Pacific going through the Arctic Ocean. The ice was pretty much like that for quite a long time, but as 2007 came around, 2007 was actually one of the worst years for sea ice. We had a drastic drop in sea ice in the North Pole and the Arctic region, and for the first time, as far as recorded history goes, you could actually drive a boat through this and get from the Atlantic to the Pacific Ocean without encountering sea ice. This was a huge wake-up call that out there's something definitely happening to our ice caps. And once again, this is a huge area, and where did all that water go? Well, it went into the oceans. Well, if you have any questions, bring them to class.